Good evening, everyone. I'm Steve Kahn, Dean of Mathematical and Physical Sciences at UC Berkeley. Tonight, I'm joined by my colleagues in the astronomy department to talk about a topic which is rather close to my heart, the newly operational Vera Rubin Observatory. I was director of the Rubin Observatory and led the design and construction of the facility from its initial stages before it was approved for funding until just before final assembly when I took on the position as dean at Berkeley. The construction of major observatories is generally a monumental undertaking, and Vera Rubin was no exception. Our team involved dozens of institutions and vendor partner organizations across the globe. This was an ambitious international investment in astronomical discovery. The heart of this facility is the largest digital camera ever built. By capturing ultra wide field, high definition images across the entire southern sky, Rubin is providing us with the most detailed time lapse record of our universe in history. This allows astronomers to discover new phenomena on a scale that was previously impossible and to make precision measurements of immense samples of various forms of stars and galaxies. I led our team as we overcame incredible hurdles to bring this vision to life. We were pushing the technology envelopes in all aspects of the design, from the telescope optics to the final data processing. For decades, we were focused on engineering the eyes of the machine, but now we finally get to see the universe through those eyes. But Vera Rubin doesn't just capture images, it stretches the horizon of our understanding. Its innovative technology allows us to investigate cosmic mysteries, such as the sources of gravitational waves and the nature of dark energy. It is a profound full circle moment for me to sit here with the very scientists who are now catching the light we worked so hard to collect. We have assembled an esteemed panel of Berkeley astronomers who are among the first to dive into this treasure trove of data. They will reveal the impact that Vera Rubin will have on the future of the field and the innovations that we are introducing here at Berkeley to exploit this enormous new capability. Before we get started, we will be taking questions after each presentation, so please add those to the chat. And now I'll turn to tonight's first speaker to set the scene. Josh Bloom is an astronomy professor teaching radiative processes and high-energy astrophysics here at UC Berkeley. He is a world expert on time-domain transient astronomy, artificial intelligence, and telescope in-sight automation. He's a former Sloan Fellow and a Hertz Fellow and received the Pierce Prize from the American Astronomical Society. His current research focuses on deploying AI tools to facilitate discovery using data from the Vera Rubin Observatory. As a deluge of data threatens to swamp traditional approaches, astronomers, by necessity, are leveraging AI methods to conduct their research. Josh, thank you for joining us this evening. The floor is yours.
Thank you, Steve, and thank you so much for your leadership, both here at Berkeley and in the run-up to this amazing moment that we have with Vera Rubin Observatory. We couldn't be here without you, so thank you again. Welcome, everyone. I have the great task tonight of laying the groundwork for my colleagues, helping orient us around the science of Rubin and some of the modern techniques that we're using to do science. And because AI is so top of mind for all of us, not just in our professional lives, but in our personal lives, I thought, what better time to tell you about how AI is influencing the way in which we understand the universe through the lens of Rubin. In case you haven't seen pictures of this amazing facility and the amazing instrument behind it, I wanted you to see just a few of those here. We are doing with Rubin celestial cinematography. Over 10 years, we'll be taking 820 or so time-lapse images of a large part of the entire sky. It is, as Steve said, the largest camera ever made by mankind, capturing in just one snap something like 40 full moons on the sky. To give you a sense of scale of the mirror, and by the way, to calm down, the mirror doesn't look like this today. This is in the early stages before it was polished. look at the size of the people here on this screen, and you get a sense of this massive 8.4 meter telescope and the enormity of the task that it took to build something like this. The telescope itself is this really innovative sort of 3-bounce surface, but done in 2 physical mirrors. And there's an actual sort of M3 mirror, the third mirror, as we say, embedded in the big one. It's a wonderful and modern design, but it is a behemoth. And as we start thinking about the science it's going to do, in some sense, it's been looming super large for us even before it got created. Over the last several decades, many of us have been thinking about the science we could do with Rubin, and only dreaming of the millions of supernovae that are going to be detected every year. And what's so exciting for me and Raf in particular, as you'll hear from her later on, as time domain scientists, is that just in February, on the 24th of this year, we were able to get our first alerts from this facility looking for new things changing in the sky. And in that one night, we got 800,000 astronomical alerts. And it's happening at full speed. And we're planning on basically seeing every supernova, every asteroid, every variable star, any unexplained flicker is happening and broadcast to the world within 60 seconds. The sheer numbers, as you see here up on your screen, of the raw data that we'll be getting, just the imaging alone, 20 terabytes per night, and tracking over the history of Rubin, something like 37 billion objects. The legacy survey of space and time, now called LSST, is going to produce something of order 150 teraflops of computation that's required to produce the first data that we'll be seeing en masse as astronomers. And so it's really kind of mind-blowing. And what's also kind of mind-blowing is that if you think of the astronomer as somebody who goes out to the telescope, we'd all love to be in Chile these days. A lot of what we do in modern astronomy is sitting at our desk and trying to do novel science using the databases and the assembly of the information of the universe that was done by others, by the great people as part of Rubin. And what I'm so I think excited about is that we're not just looking at databases, we're trying to extract novel insight. And here we're using AI in a modern context to be able to extract the information and learn new things about the universe. I look at this Vermeer painting from 1668, and I think of this as this kind of quaint view of the noble astronomer. And we've kind of come back to that picture. And maybe you could think about this as like the first Chat GPT, where it's an assembly of information about the cosmos that was done by other people, but giving this great insight to those of us sitting in our chairs. So one of the things to think about as we think about this data deluge, as Steve said, is that AI is actually already here. It's already arrived in astronomy. My first machine learning papers were about a decade and a half ago, but it was here before this. And if you look at the red curve, that's basically all the AI that was used inside of time domain astronomy. And the blue curve is all of astronomy itself. What's really exciting is that you might actually be able to make out a Moore's law kind of view of our use of AI. And it's permeating not just my own work, but the work of many of our colleagues here at Berkeley. And we're not just making use of some of the techniques built elsewhere, we're actually creating some of these techniques ourselves. But it is, just to give you a sense, all over the place. People are using AI to understand the amount of dark matter and galaxy clusters. We're using AI actually to make images of nearby black holes. AI is being used in innovative ways to actually find and understand the gravitational wave background that could be left over from the Big Bang and or colliding black holes. And even more closer to home, people are using AI to understand the atmospheres of planets outside of our solar system. So what accounts for the AI ascendancy in astronomy? And this is really kind of where I think LSSC and Vera Rubin come in. Well, one thing is to say is that if you think about us all looking at data in the old school way of thinking about astronomy, human experts don't scale. And so we need intelligent agents to work on our behalf. And the other thing is that as we wind up introducing more and more complex physics and we want to model the objects that we care about, we have these computational bottlenecks. And these are the two places that I look for in my own group as we wind up trying to figure out places where AI could not just be a help, but be the unlock that gets us to the science that we're excited about. So what I've been working on is the kind of AI in a production sense, working on real images. Here, we're interested in discovery. So we look at a raw image of the sky on the left-hand side, and in the middle, we have a static sky picture of what it should look like. And if we subtract the two, we make out this little blip, which could be a new supernova. And so using computer vision techniques to be able to uncover that and understand the rates at which these are happening and sift kind of the wheat from the chaff to find the real and not the bogus sources. That happens when you get image differencing. Once you get an object, you want to look at its time history. So we look at time and we look at flux on the y-axis. So brightness is a function of time. And we ask ourselves, is it worth spending our precious follow-up resources, not just with Vera Rubin, but the other sort of spectrographs and other imaging capability that we have, not just at optical wavelengths, but across the magnetic spectrum to actually follow this event up. And once we actually have an event and we followed and traced out its evolution in time, you might be able to make out these data points in time. Again, flux is a function of time here. We want to now compare what we observe, in this case, a supernova, to the model parameters that wind up telling us what the physics is of these, in this case, explosions. And doing this, if the actual model itself is a supercomputer amount of time over the course of weeks or months to make just one light curve, we'd like to be able to go backwards and say, if I have data, what are those model parameters? And here, machine learning has been a great help, not just at LBL, but also down on campus in the work that we've been doing within my own group. We've been using Real Bogus now almost for 15 or 16 years in the precursors to LSST Vera Rubin, and not just doing machine learning because it's fun. It's actually a little bit painful for those that have done this before. But when you work in a noisy, big, dirty, and streaming environment, a lot of things can go wrong. But when it goes right, it's super exciting. We found with AI the nearest Type 1a supernova in over 3 decades, that in 2011, using a machine learning computer vision technique like what I just described with Real Bogus. And what was exciting is that this supernova would have actually been detected and observed by amateurs a few days later, but because we found it so early, we were able to do novel science that we wouldn't have been able to do if we waited for this thing to get bright. And now Real Bogus has become really a cottage industry. And if you're going to be doing novel astronomy these days with images, you have to use some sort of version of this. What I want to just say in my last couple of minutes that I have is about how we're using AI in my group to optimize the way in which Vera Rubin is going to be observing the sky. And you'll hear a lot more from Raf about these amazing objects. But we're trying to find these needles in the haystack, in particular, after a gravitational wave event of 2 neutron stars colliding or a neutron star and a black hole. We're expecting to see, and I've seen 1, maybe 2, maybe 3 of these events in the past, this very quick, evanescent, and very faint object in the sky that's associated with this. This is the afterglow of what happens. We call this a kilonova. A lot of the great theory that was done on these objects was done here at Cal. But this is not just a needle in a haystack. In looking at one place on the sky, we have to look at large swaths on the sky. The green localizations that you see here projected onto the image of the sky are the LIGO detections from the gravitational Wave Observatory. And then overlaid that are the localizations from a gamma ray burst detector. And after just a massive effort from many of the people here and across the world, one of these little objects was found and discovered. What we want to do is figure out how, with Rubin's great wide field capability, when a new one of these events goes off, we can use it to be able to discover these new kilonovae events. And so what we've done with a graduate student in my group is take those localizations on the sky, we call them bananas, turn them into a graph neural net, and then using reinforcement learning techniques, the same sort of techniques that people are using to build self-driving car capability, to figure out the optimal way that we should be observing the sky to optimize our way to actually discover these new kilonovae. And if you can see this little movie here, we're bouncing, this is in simulation land so far, we're bouncing the localization of where LSST Rubin should be observing and which filter it should be observing in to maximize our chance of discovery of these types of events. And what's so exciting is, as we've been building out these capabilities, we wound up realizing that we were able to get better detection capabilities than the existing scheme that people are going to be using once LSST Vera Rubin starts observing the sky and doing target of opportunity observations. So I want to end with a quote from Wayne Rosing, who was the creator of the Las Cumbres Observatory Global Telescope. He said, "Those photons traveled a long way to get here, and we owe it to them to detect them." And I love this quote because it's absolutely right. It's why we build big buckets to collect all of our photons. But I like to extend this out even further. We wanted to collect not just photons, but multi-messengers, all of those really interesting objects that aren't photons, like neutrinos and gravitational waves. They took a long time to get here as well. And we owe it to detect them, yes, and collect these really, and with large buckets, collect all this light. But we also need to analyze them, and we need to do that efficiently. And this is where a lot of the work that we're doing here at Cal comes in, to be able to do science more efficiently and effectively on this massive data that we're about to start working with. So with that, I'll say thank you and say, really AI is the most powerful scientific tool of all time. This is from a quote from somebody who is at OpenAI for Science. And we really view it this way. We couldn't do this science without the great light buckets, but we also need to have, because of these computational bottlenecks and really the expert bottlenecks, we need these new techniques. And this is where we're pushing the envelope here at Berkeley. So thank you.
Great. Thanks, Josh, so much for that excellent review. And just as a comment, Wayne Rosing was one of the early private contributors, actually, to the Rubin Observatory. So he really played an important role. Let me start with a question. So you've highlighted how important AI is to this sort of science. How is it changing the way we educate young astronomers?
It's a wonderful question, right? So I think of one answer to that, Steve, is that astronomers have always been good at using new tools, right? There was this astronomer you may have heard of named Galileo, who had found out about this new thing that could look for ships coming over the horizon. And instead of using a telescope for military purposes, just went like that, right? And then lo and behold, modern astronomy. We've been doing that through the history of astronomy, using statistical inference tools that were developed elsewhere for other reasons. We've been using it, detector technologies that arose in the form of CCDs. And I think of what astronomers are as on the bleeding edge of looking out at the landscape of tools and saying, how can we use this and adopt this to improve our workflows? And this is what we teach our students: is every tool that is powerful and useful can be a danger if you don't know how to use it. So boy, we better teach you the sort of deep concepts behind that. Doing this not just in the astronomy department, but in concert in double majors and in minors with all the amazing other groups that are out there on campus. has been, I think, a great unlock for our students. We're not boxed into the old school ways of this is how you do it and this is the programming language. That's one answer to the question. The other answer to the question is that things like ChatGPT and Claude Code have really fundamentally changed the way that we think about teaching our students programming, because programming has been this sort of substrate for our students to be functional and to be able to work with large amounts of data and to express themselves as they work with data. What we're seeing now is this great unlock, not just for the students that are massively CS minded, but for those that may be much more into the physics or maybe much more into the statistics, and now they can be as functional or even more by bringing all these tools to bear. And so we're helping students, and Raf has really been a pioneer in this sense, working with students and helping them understand how we can start incorporating this into our workflow as scientists.
So we have another question from the chat. How do we control for junk AI in these codes? Do we even understand how to identify it?
Do we have a couple more hours to answer that question? I have a lot to say. And AI slop is something that we're all very worried about. One of the things that I would say is very interesting is that A, the tools are getting better and better, and B, what we're starting to learn, not just as scientists, but people that are just being functional in this new AI era, is that you can build harnesses around the work that you're doing. We're back to, for those of the programmers on this call, we're back to test-driven development. And so when we work with our students, we say, well, sometimes instead of writing the code from scratch and then building tests, what if we just started building a whole bunch of tests and then said, now let's ask our AIs to build code that actually passes those tests. And so we've kind of upended programming, but we've also sort of come full circle. There is some really scary aspects of bringing AI into our workflows, which is why we need to step into it very carefully, and why we can't just sort of download something that we found on GitHub and install it into our software project and hope everything works. It's why we come back to education and ask ourselves, do we understand what's happening? We're still writing code, or our agents are writing code on our behalf that has to have physical meaning. It has to make sense, and it has to pass our tests.
Okay, thanks, Josh. We'll have time for more questions when we bring all three panelists back at the end. Now, let me join me in welcoming our next speaker this evening, who's a graduate student in astronomy, Peter Ma, who works with Josh and also a bit with me. Peter is a second-year astrophysics PhD student at Berkeley who works on integrating AI and GPU-accelerated computing throughout the astrophysical discovery pipeline. He's currently working with Josh and me in developing and deploying a real-time AI system to help control and operate the active optics system at the Vera Rubin Observatory. Peter, why don't you take it away?
Yeah, thanks, Steve, for the intro. So, hi everyone. My name is Peter. I'm a second year grad student, and today I'm going to be talking about developing and deploying a AI algorithm to the summit of that brand new completed Vera Rubin Observatory. So let's get started. So this is a picture taken of the Virgo cluster about 20 years, more than 20 years ago, before I was born. And this is what it looked like back then. And this is what it looks like now with the first look from this newly completed Vera Rubin Observatory. And you see all this huge treasure trove of new data, data that we can then create great discoveries from, make discoveries from. However, all of that requires us to deliver on one particular promise. And that promise is that we have fantastic image quality, right? The whole point of a telescope is to take great pictures, right? And this is where the problem starts to arise. Okay, so what's the problem here? Okay, so you're looking at the thing, the optical system in the Vera Rubin Observatory, and this guy weighs like 350 tons. So kind of big. And if our goal is to image the entire night sky every 3 days in the southern night sky, we need to spin this guy around like every 30 seconds to a minute. All the while, we need to control all the alignments of the mirrors and all the equipment up to sub-micron levels of precision. So that is about 1/100th to 1/10th of the width of a human hair. And so that's a pretty gnarly task to try to do. Okay, and so if you don't do all those corrections, if you don't, correct for all those problems, your stars that should look like something on the left kind of look like some things that are on the right. And those are not good for us to do any good science with. And so in the end, we want our multi-billion-dollar telescope to deliver on all those great science goals that we're super excited about unveiling. So what do we do? So a lot of smart engineers came up with this idea called an active optics system. So how does this work then? Okay, so you're staring at is the camera that Josh has just shown you. You're staring right down into the barrel of it. In the back, there's a bunch of CCDs, most of which is used to take beautiful pictures of the night sky, except for these stubby little corners on the edges here. And they're used to do absolutely no science at all, and they're supposed to do what we call a curvature wavefront sensors. Okay, so what are these? These are basically chips, or CCDs, that are permanently pistoned out of focus. Okay, so you see them here physically exposed. And so you're probably wondering to yourself, okay, Peter, why in the world would you want to look at things out of focus? Well, just like when you take, say, a DSLR camera and say you take a picture of something out of focus, things that should look like points look like blurred circles, for example, here. You can do the same thing with our telescope, our super expensive telescope. So if you were to blur out the image, go out of focus, your stars that should look like points eventually look like donuts. Okay, they're donuts because the pupil is an annulus. That's the only reason. Okay, and so why would you still want to look at out of focus images? Well, it turns out the out of focus donuts that you see here tells us something important about how performant our optical system is. More specifically, the unevenness, the lumpiness, or the weird shapes of the donuts tells us about how much aberration there is. And then you can conceivably think of a control algorithm that you can then piston and drive the optical system to correct for those. And so behind all those mirrors, so when you see Josh with that picture of that huge mirror, behind all of those are all these individual pistons and actuators that then drive and move and change the shape of the actual optical system to correct for all those problems that we talked about. Okay, so I painted this picture is that if you can estimate these corrections, you can just win this game. So how do we do this with the classical model? So traditionally, we have an algorithm called Danish, which is just a classical algorithm where we brute force various trials of what these aberrations are. And we take the one that's best fit, right, basically, of those aberrations. And the performance is not too great. So what you're looking at here is a distribution of the degradation of the PSF. You basically want everything on this plot to be at the left-hand side of this gray dash line. And this is done in simulation, and we see that we're not really there. We're about there 1% of the time at optimal alignments, right? So my task is to try to make this better than the 1% situation that we have right now. And I think we're pretty much close to getting there. So this is not good news yet. Okay, so what are we proposing then? So we believe what we can't solve with our theoretical models or these classical algorithms, we may be able to solve this with just data. And the data-driven approach usually involves some kind of learning algorithm. In this case, it's a neuroactive optics system, so we're proposing. Okay, so how does this whole thing work? It's very, very simple. There's 3 main steps. The first step is to just find me the donuts. Okay, so given an image, find me and crop out for me all these donuts that you see in the frame. Okay, great. Then what you want to do is you want to then look at individual donuts, give an estimate for the aberrations, and tell me what that answer is. Now you can leverage the fact that individual donuts should all estimate the same wavefront. You can come together with a global aggregation, attending across all those images, and get a best fit result. And we see that on the same curve, we're doing so much better than what we were before. And that's pretty exciting. We're hitting about a 70% success rate, which is much better than the previous 1%-ish in simulation. And so this gave us some confidence to try this thing on Sky. Now, does this mean we win, Peter? Is this the end of the story? And unfortunately, that's not even close. And so out of all the engineering problems that we have to deal with, I'm only going to talk about one of them today. And this is about runtime constraints. Okay, so these are the computers on the summit at the observatory. And as Josh has pointed out, they're chugging about 20 terabytes of data every single night. And my goal is that I want to make sure that all the computing resources are allocated to science, right? And so I really want to challenge this myself and see if I can make this run on a single CPU core to estimate the entire wavefront every 10 seconds, okay? So we want to see if we can demonstrate maximal science capabilities on such low-power devices. And for those who don't work on developing or neural networks and who don't or find it hard to empathize with my situation that I put myself in, I went on Amazon and found a Ring doorbell camera that supposedly has the same specs of my original proposed one single CPU core, right? That also supposedly has AI on board. So somehow I need to make the algorithm run on something that is as tiny for you to figure out when your package is arriving to then operating one of the world's largest observatories ever built by our species. So this is a crazy challenge that, fair enough, right? This is what grad school is all about, I suppose. And so we will throw everything in the book at this problem, particularly things from industry, things like layer fusion, just-in-time compilation, neural architecture searches. We eventually, in the end, were able to hit the sub 10-second mark on that one single CPU core, which is pretty exciting because then this gave us the green light to try this guy on Sky and see what happens. So let's deploy, let's see what happens. So very recently, we were able to deploy this on Sky, and for, I think, 30 minutes, my black box neural network was controlling and moving a multi-billion-dollar instrument. And so what you're looking at here is my model converging towards focus. And although we weren't able to hit the eventual goal that we wanted to, we needed to correct for some offset. So we need to go back and debug our model and also go back on Sky again. But we do want to highlight that we were able to maintain incredible stability of the entire optical system throughout our entire testing regime. So much so that some of the engineers are saying that they've literally never seen this even happen before with the classical models, which is really promising given by the fact that there's teams of people working on this, and there's just me working on this black box neural network to try to make this thing work. So it's pretty exciting. And it's also very, very hopeful that we may be able to, in the end, win this problem. Okay, so I'm going to close off just to say that doing AI for astronomy is hard, but also doing useful science with AI is also even harder. Deploying things onto real things is not easy at all. In the end, we can beat benchmarks day in and day out, but in the end, we wanted to do actual science for us, right? In the end, I just want to highlight that, whenever you're developing neural networks, it's easy to see that it's, people, work with these offline and, there's very little risk involved. But when you're working with, expensive equipment, you do a lot of guardrails and safety checks, which is really, really important. But yeah, with that being said, I'll happy to take any questions.
So thanks, Peter, for a really great talk. And yeah, this is what we try to do at Berkeley is to get our graduate students really into the key things that are facing the field. So this is a wonderful contribution that Peter's made, and we're gonna get it working on the telescope regularly, and hopefully it'll be the main way to drive it. Peter, let me ask you a question. What kind of data did you use to train your model?
Yeah, so the main algorithm was trained on simulations. So we have this crazy complicated simulation that ray traces a beam of light from the beginning of time through the universe, through the atmosphere, and then through the optical system, and then simulating the CCD physics. And then we brute force maybe 10,000 of these images. And then we train our neural networks on those. And so with these high fidelity simulations, we then coupled it with real commissioning data from the past year-ish to condition our model to be robust to, the outliers that you see in real data, like hot pixels, things like that. And so it's a mix of real data and also high fidelity simulation data that we were able to use in the end.
And so the atmosphere is affecting the images. So how do you know what the atmosphere is doing? How do you take account of that?
Um, that's a good point. Also, we tried to simulate out the effects of the atmosphere in our simulator. So in our simulator, we can set, for example, the atmospheric PSF that we expect. And then hopefully that is enough to cover the grounds. We also take into the fact that we are using real data sampled from a variety of nights to also take into consideration of what actually the scene would look like at the summits over the course of a couple months, for example. And so in those regards, we folded in that information that way.
And the question from the chat, how are you avoiding selection bias in that process? Is selection bias a concern for this?
Yeah, that's a totally valid point. So one of the, I suppose what you're trying to get at with the selection bias is that how are you simulating the original parameters to generate all the simulation data? So what we did is we took the Costco model, which was running for about a year, and we basically sampled a whole distribution of possible wavefronts with these parameters. And we use that sampled wavefront to then draw the actual simulator. So we're sampling hopefully from a realistic distribution of what the wavefront will look like at the summit.
And could you comment, there's another question in the chat, could you comment on how does this compare to what people may have heard about with laser guide star adaptive
Yeah.
optics? What are the differences?
So yeah, so the key thing is that adaptive optics is operating on the order of kilohertz, so very fast, and their goal is to basically try to optically delete the atmosphere is what they're trying to do. Whereas for us, we're trying to correct for the intrinsic optical aberrations in the system itself. So we're not actually trying to correct for the atmosphere. And so that being said, we are um, operating on controlling the pistons on the order of maybe once every observation. So on the order of seconds to minutes time scale, so much slower. And the goal is to not correct for the atmosphere, is to correct for the issues in the telescope itself.
Okay, thanks, Peter. That was a great review. Now we have to turn on to our next speaker. Keep adding questions, and we'll pick them up again when we bring all three speakers back. Now we'll turn to our final speaker, who's Associate Professor of Astronomy and Physics, Raffaella Margutti. Ralph Margutti is the Mark and Christina Benzadune Professor of Astronomy and Physics at Berkeley. Her specialty area spans astrophysics, compact object mergers, core collapse supernovae, gamma ray bursts, neutron stars, radio astronomy, space astrophysics, stellar evolution, supernova shockwaves, supernovae, and tidal disruption events. Basically anything that goes bump in the night. Her research is positioned in the new field of multi-messenger astrophysics with gravitational waves and other messengers. Margutti received the 2022 New Horizons in Physics Prize for leadership in laying foundations for electromagnetic observations of sources of gravitational waves and leadership in extracting rich information from the first ordered collision of two neutron stars. So, Raf, please take it away.
Thank you, Steve. And thank you all for having me tonight. So my goal is in the next 8 minutes or so to give you an idea of what exciting science we are hoping to achieve as soon as Peter fixes the telescope for us. So astronomy, discovery in astronomy is pretty much enabled almost always by the deployment of new capabilities. And in the case of Rubin, in the case of this gigantic telescope, this has to do with the capability of exploring the fourth dimension. So for the first time, we can ask ourselves the question, what is there in that direction in the sky now that wasn't there 2 hours ago? So this is the first time that we can really probe this question to a depth that is pretty much unprecedented. So what makes this important. So we always have to ask the question of why. And why has to do with the capability to answer to some fundamental open questions that we have. So here I'm going to pick a couple of directions to give you an idea of what we're trying to achieve. So for example, we know that stars explode, but we do have big question marks about what type of star explode, like what type of stellar explosion, and what happens to these stars in the final moments, in the final years before they go boom. Equally important is the amount of ignorance that we have on the other side of the question. We do know that massive stars like to hang around in binaries. Some of them are able to stay together until the end, and then they merge, they become neutron stars, and then they merge. And now we can detect their mergers through gravitational waves. But we have a very fundamental question that is still very open, which is how do they look like if we try to observe them with light? And it is a combination of Rubin capability of monitor the sky in the time domain, so temporal coverage, together with the unprecedented sensitivity that allows us really to do completely new things. So today I'm going to focus on two things that I think are going to be extremely exciting in the future. The first direction that I want to emphasize has to do with what happens in the final years before a star explodes. And I'll try to give you a feeling of why Rubin will actually completely revolutionize this field. So what you're looking at there is a map of this stellar explosion that happened. In spite of the name, it actually happened in 2012. And when I was in my PhD almost 20 years ago, the lecture that was given was that stars would just wait quietly, sitting there, not doing anything until one day they would explode. Nature, however, had some more interesting plans and actually revealed that stars are not quiet at all before they explode, but they experience this number of outbursts. So they go up and down in the days before the major explosion. So for Supernova 2009 IP is pretty much the first event that actually sent the communities this very powerful message that yes, stars are not quiet before they explode. However, at the same time, we had images of the star that was producing these fireworks, and it happened to be an extremely massive star, like more than 60 times our own sun. And so at that point, we were left with a big question, which was, yeah, okay, we know that this star experienced this outburst, but maybe that is something that only happens to the most massive stars. These are way less than 1% of all the stars in the sky. Why should I care? However, in 2022, here at Berkeley, working with Wynne Jacobson-Galan, was actually my grad student here, now Hubble Fellow at Caltech, we were actually able to demonstrate that this type of fireworks before the big explosion was common. And what you're looking at here with that light curve is the most common way a star can explode. We call it type 2p supernova. We went back to the images that we have taken with a survey, the Panzer survey, and what you're seeing right there in those images is that source that goes up and down. This is evidence of pre-supernova eruptions. So at this point, we were convinced that all stars pretty much do experience these eruptions. And at that point, you might have a question in your mind, because I told you all stars do it, but how come it took all the way to 2022 for us to figure it out? And the answer is the simplest thing you can think of. What you have right there is a plot of brightness versus time. You can see in gray these very massive stars, and before the big explosion, you can see those little bumps. And these get very bright, so we can see them very, very easily. But for most of the stars, actually, the sort of eruptions are very weak. They are faint. And this is where Rubin is going to effectively reveal the life of these stars before stellar death. And that is going to be completely revolutionizing our understanding of what these stars experienced before the big explosion. Now, on the other side of the game, what happens after a supernova explosion? So let me tell you a little bit about why we are so excited about interrupting the Rubin survey. And I'm going to try to convince you that we do so only for very, very good reasons. So, okay, so here it is. So we want to understand effectively what happens after these explosions. We want to understand how these collisions of neutron stars, what type of light they produce and how they evolve. And I believe that this audience will be already very familiar with the fact that in 2015, we have detected for the first time gravitational waves from black hole mergers. And 2 years afterwards, in 2017, we had the first detection of a neutron star collision together with light. This is the beginning of a completely new era of exploration. And what happened was an amazing triumph of theoretical predictions. What you're seeing right there in red, this is the model that Professor Dankesen here at Berkeley actually predicted about how light will be distributed. Here we're looking at the near infrared. And then you can see in black, those are data that another professor here at Berkeley, Ryan Chornock, acquired for this particular event. So very good predictions that we were able to verify immediately as soon as we had a chance. But 170817 was extremely nearby, really around the corner from an astronomical perspective. So one thing that we learned very clearly from 170817 is that these counterparts of neutron star collisions are very faint. And that's where Rubin comes into play. So not only these counterparts are very faint, but gravitational wave instruments are not very good at telling you where to look. So they tell you, well, the gravitational wave came from some part in the sky right there. So let's assume that this part is what you see there with the gray circle. Inside, you have a lot of potential sources that shine with light. So the game here is a game of having to go and pave this entire area. And that's something that Rubin can do very, very quickly and efficiently thanks to the very big field of view. But Rubin can also go deep. And so we'll be able to tell us which one among these many possibilities is the counterpart. So very early in the game, we understood that the Rubin Observatory could be really a game changer in this hunt for neutron star collisions only if equipped with this capability of interrupting the main survey. And that's what we call target of opportunities. This is something that, again, is very Berkeley centric, I would say. Back in 2011, you can see that Josh led this effort where he said, look, if LSST and Rubin are going to do something interesting, that is going to be about gravitational wave sources. In 2015, I joined the Rubin collaboration and started leading the multi-messenger group and started pushing for the deployment of this target of opportunities. We kept pushing other papers 2018, and then something very crucial happened here in Berkeley in 2024, where we had an entire community worldwide that got together, and together we were able to convince the project to give us 3% of the Rubin time to follow up these sources, which is a major achievement. And the story continues, and it continues again here in Berkeley later this month, where the entire community is going to come together and we're going to start thinking about what is the best way to follow up these sources and try to understand what physics is behind. And you heard from Josh that Josh has some very great ideas about what is the best strategy to do so. But let me tell you why I think that this era of time domain astronomy is going to be particularly interesting. And let me tell you why I do believe that here at Berkeley, we can play that game to the highest possible level. So by now, I think you're convinced that a discovery engine in time domain astronomy right now is no longer just a telescope like Rubin, but you need to add to that telescope some theory-informed anomaly detection or AI. So I need to have Josh that tells me this is astrophysical, this is trash. But also I need AI to help me out understanding which among the many astrophysical events are of interest. So what we do is that we do have all the expertise in-house here to filter through all of these hundreds and hundreds and hundreds of potential events. And only once we find the object of interest, here I was playful, I just identified a supernova that also has a very Berkeley history. Only after you have identified something of interest, we repoint all the facilities, and that's where that is the main expertise of my team. And very excitingly, there are two newcomers, UVEX, again, something that Berkeley is highly involved with, that will be launched in 2030. And we have a new survey, LS4, that was also born here at Berkeley and is going to be starting operation later in the year. But so right now we've found an interesting source. We have characterized it by collecting all the possible photons I could think of. And then the third very important step is a step of interpreting this data and trying to understand what physics is happening right there. And this is where our colleagues, Professor Dan Kaysen and Professor Wen-Bin Liu here at Berkeley are actually the masters. And then this interpretation feeds back into the theory-informed anomaly detection algorithms and closes the loop. So it is this combination of having a discovery machine right there that is able to pave the sky, together with multi-wavelength perspective that is able to help us understand what's going on. It is this combination that is what is going to lead to really amazing progress in this field. And to achieve that, we have put together a new center. Our dean has been very supportive, and I'm very lucky to be director of this center right now. And I'm gonna just close with this slide. I just want to emphasize how progress will rely on basically tearing down the barriers between disciplines. Literally, this synthesis of information is future. Thank you so much.
So, thanks, Raf, for an excellent overview of a very exciting field of astronomy. So if you can see these pre-eruption modulations in supernovae, will you be able to predict when the actual supernova goes off?
This is exactly the end game. So we want to get there. Our goal will be to learn enough about what those stars experience in the last years of evolution to actually be able to predict the explosion. Yeah, it is exactly the end game. We are very far from it, but I think Rubin will take us there.
And how many more neutron star mergers are we going to get?
Okay, all right. This is so as you noticed, after 2017, we were not able to find another neutron star merger, and that's just we have to live with that. That's the rate of neutron star collisions that the universe is giving us. So the good news, though, is that later this year, the gravitational wave observatories are going to come back online. So right now, they're actually offline to improve their instrumentation, but they're going to come back online in the second half of this year. And the prediction is 1 to 3 during the next 6 months. But it's Poissonian statistics, so it's possible that we might end up empty-handed. But if it happens, we will be absolutely ready to make the most of it.
Yeah, we need to build a machine to make them occur more frequently. How will we do that? In any case, so you talked about a lot of different things. What are you most excited about possibly discovering from Rubin?
Yeah, I do think that the possibility of identifying neutron star mergers from Rubin data alone. So saying, suppose the gravitational waves or the gravitational wave instruments are offline, how can we maintain that field alive? I do think that there is a possibility to actually try and identify these mergers just based on Rubin data. And if we succeed there, that would be an amazing achievement because the rate of contamination is extremely high. So it's an interesting problem from many different perspectives.
Great. Okay, so thanks, Ralph. Now we'll make a quick transition and invite all three of our speakers back up. And hopefully we can address a few questions to the collection of them. An interesting question came in the chat. How will the Starlink launches affect Rubin science? Anyone want to take that? Josh?
Steve, I'm guessing you're in the best position, having thought deeply about that, and you're more political than we are.
So let me say that there is, for those of you not aware, there's a planned explosion in the number of artificial satellites that will be launched in the near Earth orbit over the next few years. This started with telecommunications satellites like Starlink, for which there are now tens of thousands. Um, there are plans to launch data centers into space so that we can meet the demands of AI without dealing with all the power and cooling issues we have to face on Earth. That argument, I think, is a little less clear that that's worthwhile, but there are companies planning to do that. This could get really bad, just to understand the implications. It's possible if you take these companies at their word that there would be enough satellites in low Earth orbit that the sky would never get darker than half moon anywhere on Earth. And so it would be humans would lose the ability to look at the faint dark sky. And of course, astronomical research would be heavily impaired, including from Rubin. We'll see how this goes. We're trying to generate reactions to this, so feel free to write your congressman how bad this would be for humanity, for astronomy. But it's one of the things we're dealing with. In the near term, the satellites that are already up will leave streaks in the sky, but they won't impact most of the observations that we have. Let me ask a question for you collectively at Berkeley. Raf, you talked about the center you're forming. How are we as a university, as a campus, arranging ourselves to lead the world in this field?
Yeah,
Raf
maybe
or
I can
Josh?
take that one. Yeah. So I think that what makes us unique is having the entire ecosystem that I described. So having real experts in every possible aspect, from AI to actually improve our instruments, as Peter is doing, to employment of AI to find sources of interest, to following up the sources of interest and to model them. So I think that our unique strength is that we have all the players in the same place.
I guess I would just add, agree 100%. We also live in this amazing environment around other departments and other colleagues who are thinking about AI, for instance, not just in terms of optimizing ad clicks, right, but in thinking about the impact for society, thinking about the ethics of it, and innovating algorithms that we all need. One of the things that I think is very unique about Berkeley is that, which has its ups and downs, is the interdisciplinary nature that is really from the bottom up. So faculty find each other, and we want to work together across departments, across disciplines. And those become deep and natural kind of collaborations. And our students have access. For instance, Peter is working with some of the folks at the Berkeley AI Research Group there. And when we got a problem here and we don't know how to solve this, how do we take this 200 million parameter model and shrink it to 2 million? It's not just going online and watching YouTube videos. It's actually going across the street here and talking to people who are innovating and creating those algorithms. And it's not just us talking to the computational folks, it's also them talking to us. And they are seeking out really interesting, hard challenges. We have different types of data than they're maybe used to in industry, different types of questions. We're interested in causal inference. We're interested in uncertainty quantification. We're interested in problems that are not natural in many industries, but are just incredibly central to the way that we think about doing inference in physics. I was just at a retirement party right before here for a statistician, and I realized, his name is Philip Stark, that every time I had a crazy idea over the last 2 decades that involved something with statistics and AI, I would always ask him. And he was always my gut check. I've got more folks like them now in my orbit. But we're so lucky to have our colleagues here in the astronomy department in physics, but also more broadly at the university.
Great, thanks.
Yeah.
And one final question, Peter, what excites you most scientifically after you get the active optics system working on Rubin? What do you hope to discover?
Yeah, so broadly speaking, I'm agnostic to any kind of like astronomy problem, really. I'm really excited about taking all these advanced algorithms and applying them to do cool and interesting science. One of the current many projects I have with Josh involve trying to look for signs of Planet Nine to trying to invent a new telescope to try to like do all these crazy things with artificial intelligence, all these cool algorithms. So gotta pay attention to my thesis in the next 5 years to see what I'll be up to, but
Right.
still in the making.
Okay,
Yeah,
sounds good.
if we find Planet Nine, you'll all hear about it. I'm sure we'll do
Yeah,
another.
you'll also hear about that. Yeah.
Okay, great. Thanks, you guys. Fantastic panel. Really interesting presentations. Looking at the clock, though, I believe it's time. That's all the time we have for questions this evening. In my opening remarks, I mentioned what a profound full circle moment it is for me to watch the Vera Rubin Observatory finally open its eyes to the universe. But as Josh, Ralph, and Peter have so brilliantly illustrated tonight, building the observatory was only the first mountain to climb. The new challenge and the new thrill is navigating the data this facility produces. To see Berkeley faculty and students standing at the absolute forefront of this new era of astronomical discovery makes me incredibly proud to be part of this work. The universe is incredibly vast, but with the Rubin Observatory capturing the data and brilliant minds like the ones you heard from tonight interpreting it, we're closer than ever to unlocking its deepest mysteries. Thank you to Josh, Raf, and Peter for sharing your groundbreaking work with us. Thank you to Danielle and our team behind the scenes for bringing this event. And I think that brings us to the end. So fiat lux and go Bears.